Good afternoon, everybody, and welcome to today's joint astronomy colloquium. Before I introduce the speaker of today, I would like to ask you to please switch off your video. And if you have any question for our speaker, please write those questions in the chat. I will read those questions out loud when the talk is finished, and I will moderate the discussion then. I am now more than happy to introduce the speaker of today, Professor Paola Caselli. Paola Caselli studied astronomy in Bologna, where she graduated in 1990. In 1994, she obtained a PhD in astrophysics at the University of Bologna, after spending 9 months as visiting students at the Ohio State University, working with Professor Eric Herbst, and 2 years at the Harvard-Smithsonian Center for Astrophysics at the CFA, working with Professor Phil Myers. After a postdoctoral fellowship at the CFA, in 1996, she became a researcher at the Arcetri Astrophysical Observatory in Florence, where she remained until 2005. 2006 and 2007, she was a visiting scholar at the Harvard University. And in 2007, she became professor of astronomy at the University of Leeds. In 2013, she was granted the ERC Advanced Grant, and since 2014 she's the director of the Center for Astrochemical Studies at the Max Planck Institute for Extraterrestrial Physics in Garching, and she's honorary professor at the Ludwig Maximilian University in Munich. Her group, the group that she leads here at MPE, consists of observers, theoreticians, and experimentalists, all focusing on astrochemistry and its applications in the field of stars and planet formation. Paola, the virtual stage is all yours.
Okay, good afternoon, everybody. I'm very happy to be able to do this JAC today and be able to tell you a little bit about our work here in Garching at the Max Planck Physics. I helped once in this. I'm really so. Let me start first of all to thank the Max Planck Society to actually be able to make up and to basically build up a group here, including laboratories, which I hope you have been able to see a little bit in the previous movie, the entertainment movie. And I would also like to actually thank the Chalmers University and Onsala Observatory for providing me with the Hasselblad guest professorship, and also University of Groningen for the Blau professorship, which is a great honor for me for this year. So what I will do today, I will try to bring you from the very beginning, so molecular clouds, where all the ingredients of stars, planets, and life are there, and down to actually protostars, protoplanetary disks, and our Earth, a little bit, I mean, our solar system. Of course, the journey that we are going to take is very long and complex, and we will see that on the way we found very interesting interconnections and very interesting complex processes that we need to take into account to actually understand going through the, say, history or our astrochemical origins, as I like to call it. So first of all, let me start with okay, so here I start with the table of interstellar molecules that have been detected so far. So these are about 200 as for, say, from February 2020. So you can see here that we go from small molecules up to significantly larger than, say, 8 atoms. Here we have also C60, C60+, And many of these molecules are actually very important precursor of what we know as, say, prebiotic molecules. For example, just pick one. This is the amino acetonitrile that was detected more than 10 years ago in Sagittarius B2 in our galactic center. You see you have 2 carbon atoms, 2 nitrogen, 4 hydrogen. Well, this is just one step away in terms of reaction from glycine, which is the simplest amino acid. Interestingly, recently there have been some effort actually, in fact, to connect this prebiotic chemistry with the so-called, say, RNA world, that we think is actually what happened at the very beginning, just before, say, life originated. And here in this complex figure that you can look into more detail looking at the paper by Jimenez Serra et al. From Madrid, they actually compiled a list of molecules, organic molecules, prebiotic molecules that have been detected. So these are the ones that you see with these black contours, and those that need to be detected to connect to the endpoints here, where you can see actually nucleobases, nucleotides that are basically the ladders of the RNA and DNA. Now, this is, of course, very interesting and important also because we know that in the primitive material of our solar system, there have been we have found, I mean, lots of prebiotic molecules, including amino acids that, of course, are the building blocks of protein, but also fatty acids that are the building blocks of, say, cell membrane, nucleobases like guanine, adenine, and uracil that have been identified. And one thing that it's always good to remember is that, at least on our Earth, only 20 amino acids are used for, by, say, living beings, including ourselves. So how do we get here? And this is, of course, a big question. And how do we move forward from that? Because once you have actually planet forms, you know, at least from the history of our solar system, that our Earth has been bombarded for almost 1 billion years after its formation by large bodies, small bodies, comets, meteoritic material, carbonaceous chondrites, all of them who have brought volatile onto the surface of our Earth. And in fact, there are some theoretical studies that show that once you start with these building blocks, you can actually form RNA polymers in a very short time. So in this paper here by Pierce et al. In 2018, they found something like that RNA formed more than 4.17 billion years ago. If we think that our Earth is 4.5 billion years ago, you see that it could take really little time to actually start the RNA world and then the first steps toward life. Of course, here I'm not, say, working actively on this, but I rely a lot on this, on the Origins Excellence Cluster that is actually I'm very proud to be part of, and that includes also people who are actively working on origins of life. Now, what we do here, we do everything we can to actually understand. So first of all, to exploit all our knowledge about molecules that we can reproduce in our labs to study regions, starting from, as I said, the very early phases, pre-stellar cores, molecular clouds, down to protoplanetary disks, and maybe in the future planets. And to do that, we need to make observation. We need to use very sensitive, very good telescopes, and here I put the two best for our purposes, the NOEMA and also ALMA, of course. Then we have to do models, we have to do theory, we need to do physical, dynamical processes, including also astrochemical processes, because when we look at clouds, we know that these clouds contain magnetic fields. And then it's very important to understand the ionization fraction in these regions, and to do that you need actually to study, to understand a bit the chemistry that is going on. We also, of course, work on chemical models, radiative transfer, and also some theory on collisional rates that actually also are connected to the laboratory work. So what I will do today, I will try to take you through this journey from dark clouds to stellar systems like our own, starting with pre-stellar cores. And I particularly like this pre-stellar cores because we now start more and more to see that some of the things that are made in these very early phases are then found also in much later phases. And I will show you this later on. I will also put some emphasis on the importance of cosmic rays. They accompany us all over time and space from the beginning, from the very early phases of clouds, down to protoplanetary disks, planets, and later on also when say maybe during the formation of life later on. Deuterium fractionation, that is an important diagnostic tool for the darkest places of these regions because not much is left there, as I will show you. I will talk about these complex organic molecules, and we always have to say what do we mean by complex. So these are molecules with more than 6 atoms, which may not be considered complex for people who work, for example, in biophysics. So let me start with the image, the picture of our Milky Way galaxy. Here you see that besides the many stars, the bright stars, you also see lots of striation, lots of dark regions, and these dark regions is exactly where the new generation of stars and planets will actually form. And to study this, as you can see, optical lights is not very good because here we had very little energy present. So we have 10 Kelvin in temperature, volume densities of about a few thousand per cubic centimeter. We are talking about H2 molecules, so that is the most abundant molecule, of course. But then if you have a telescope, a radio telescope, actually not even a big one like this one, which is 1 meter size, that actually was able to map, where the two twin telescopes, one at Harvard and one down in the southern hemisphere, to map the whole galaxy. And you can see that where it is dark, it is now bright. So molecules, first of all, one thing that we learn here is that organic chemistry is definitely going to be present everywhere where it is dark and cold, because CO is in fact the simplest organic molecule. But the other thing is that you basically need the molecule to study these regions. There is no escape, because only with the molecules so you can actually understand how these clouds move, how this cloud collapse, and how this cloud form stars and planets. Now, of course, you can also use the dust, but of course, you can't use the dust to do kinematic study. This is an example from Herschel's fire that show actually a little piece of this torus molecular cloud, where we have, in fact, our pre-stellar core that we have studied. This is our space laboratory, in a sense. Besides the laboratories that we have here, we have our space laboratory, which is this torus pre-stellar core, very dense, very bright in molecules. What we have learned from years of studies here using the IRAM telescopes is that these regions, as I said, they're really cold. In the center, there is not much left except for deuterated molecules and some nitrogen-bearing molecules. The rest of the cloud that it's here, where it's a dark cloud zone, this is more like standard chemistry, and you can find molecules, of course, like CO, HCO+, etc., that are well known by everybody, also say the extragalactic community. So here, the important physical properties that we found again some years ago, and this is a very important result, is that the temperature in this course is not just staying at 10 Kelvin constant. There is actually a decrease of the temperature if you move toward the central regions, the central few thousand astronomical units, where basically all the action will take place, where actually your future star and planets will form. What is the temperature? Well, the temperature was measured with the VLA in 2007, and the temperature was about 6 Kelvin. This is what we measured toward the center. And this implies, of course, a very large molecular freeze-out. So in 1999, we found that more than 99% of CO molecules are actually disappearing from the gas phase and are in ice. So you expect to have some thick ice. This boosted the deuterium fractionation. I will show you later how this happened. And this, in fact, the D/H ratio in this region is significantly larger than, say, 20%. You have to compare this 20% with 10 to the minus 5, which is the D/H cosmic ratio. So you need to think now, here you are in the center just before the star is formed. You have your grains, sub-micrometer size grains, surrounded by icy mantles, most likely thick icy mantles, maybe porous icy mantles, but they are, say, thick and rich in molecules, including, of course, water that is already present in the earlier stages, and CO and other complex molecules. So we know that there are pretty thick icy mantles, because in fact with Herschel, within the WISH project, this was the water in star-forming region with Herschel, led by Evin van de Soek. So we did this study, very high sensitivity study with high spectral resolution of, toward the pre-stellar core to look at water. Of course, it was not so easy to convince people to give us time, because they say, why you want to look at water where if even CO is frozen? I mean, we know that the binding energy of water on top of these grains is actually so high that you don't expect to see anything at all. In fact, it took 13 hours of Herschel. And this is, I was really happy to actually being able to see this emission. I mean, we did some calculation before, so we were expecting, and this was also thanks to Eric Quito, who worked with me on this project together with the WISH team. So we had this prediction that because the cloud is contracting, we should be able to see at least the blue wing of the line, so the part of the cloud that is coming toward us, and we should see this in emission, because the central region of this course are high enough that allow water to, say, emit photons. So you need at least 10 to the 6 per cubic centimeter of density. And then you see this beautiful inverse P Cygni profile from which we could learn so much. One thing, of course, we learn is the kinematics. So we could detect, even with the beam of Herschel, was 40 arc seconds, we could actually unveil the infall, and we knew it is a subsonic infall. Everything is moving very gentle within the central 1000 astronomical units. Of course, we measure how much water vapor there is, and this is very little, 0.5 Earth masses. However, to reproduce this with our model, we needed to have at least 2.5 Jupiter masses of water ice. So you have to think that all this ice will actually end up on top of the future protoplanetary disk. So you have the water already in large enough amount to seed the future planets that will form. The other thing that we learned, and that was also very important, is that cosmic rays need to be in the model. Otherwise, we can't have this water in the gas phase. What the cosmic rays do? The cosmic rays excite H2 molecules. The H2 molecules fluoresce back to the ground state, and they producing these fluorescence, these UV photons that can actually photo-desorb water molecules. And this is just to give you a feeling of what is going on. So this is our interstellar dust particle. You start with this naked silicates or carbonaceous material, on top of which hydrogen atoms like a lot to move around and meet and form H2. In fact, this is how H2 is formed in our galaxy. Once this dust enters the dense regions, you actually have still this core of material, carbonaceous shell or silicate core, but also, as I mentioned before, a thick mantle of ice. The CO molecules are converted very quickly to methanol because they can be hydrogenated up to methanol. There is no other electron valence present, so you cannot go beyond the methanol. The same is true for oxygen. It can go to water, and that's it. In fact, that is what we see. We see water ice, we see methanol ice, we see CO ice, and other molecules. And then you see a lot of processes like photons that are interacting photons, as far as we understand, also from laboratory experiments. Only the first few monolayers are affected by photons, but for example, energetic particles, they go much deeper. And for this, you can see this beautiful 3D image of, so we are at the scale of a dust grain now. So I took you from parsec to submicrometer size. Maybe it was a bit too quick, but just to show you here that once you have a cosmic rays that strikes on the surface of a dust grain, in this case is a proton, what you have, like for example, a few hundred keV proton, it strikes onto the surface, and what it does this trace here, and these red points are basically the secondary electrons that are produced during the passage of this proton. And what these secondary electrons do, they of course break bonds, they increase energies, for example, they excite the molecules, and you can have very interesting chemistry going on. And this is one of the things that we are studying here with the help of Alexei Ivlev, and also now with Chris Schindler-Decker, who is a Humboldt Fellow. He did his PhD in Virginia with Eric Herbst. And you can see here several studies. We are still working on these, and these are the works that we published in 2015, where Alexei actually calculated what happens if you have, for example, a certain energy, say a certain cosmic ray striking a dust grain. And you can see here that unlike UV photons, cosmic rays just go through and do a lot of damage, at least in the, say, this cylinder where they go through. And you have, of course, high temperatures there and very interesting chemistry. And here you see still again these secondary electrons. This is actually a simulation that Chris did to reproduce experiments that were done on O2 ice, again with 100 keV protons. So you can see here, for example, if you look at the methyl formate, this is actually a very ubiquitous molecule in the interstellar medium. You see it everywhere. So this methyl formate, if you include this radiation chemistry from Chris, you can enhance the abundance to, say, orders of magnitude compared to what you have without cosmic rays. And this actually goes very close to what is observed. A recent thing that, again, it's, I think, very important for our trying to really link the various phases is about sulfur chemistry. There is, I'm not going to go through the history of sulfur, but this is one of the big problems of astrochemistry. And sulfur, we don't know where it goes. Okay, this is the basic point, because at some point we see it, all the sulfur in the fused clouds, and then we don't see it. 100 times less abundance in dark regions. So where does it go? It can go in, say, all in volatile, for example, volatile molecules in ice, because then we should see it later on when you are close to a protostar, because of the ice will evaporate, at least in the region very close to the protostar. So it probably forms something that is much more refractory, much more difficult to say to remove from the grains. And in fact, Chris, what he found recently is that if you include this radiation chemistry, so the bombardment of protons, cosmic ray protons on the ices, you can actually form a significant amount of allotropes of sulfur, and in particular S8, which is the most stable species. And what S8 does, it just is stuck on the refractory material. So when we think about, say, if you want to follow the history of dust grains, you have to take also this into account, and the fact that your dust grains that are the building blocks of the planets will actually also have some significant component made out of sulfur, and in particular S8. One thing that cosmic rays do besides, of course, chemistry, starting the astrochemistry, because in fact they ionize H2 molecules, and after that you actually start the whole chemistry business in the interstellar medium. What they do, they also affect the dust charging. So this is again work by Alexei Ivlev, and here it shows the spectrum of protons and electrons here, cosmic rays, as a function of force of energy, and here for the low and high different extrapolations, say spectra for the protons that are used in general to reproduce, for example, diffuse cloud cosmic ray ionization rates, and this is what is actually observed now with the Voyager 1. These are the data from the Voyager 1 here. Anyway, if we include cosmic rays even in dark regions, I already told you that cosmic rays are actually producing UV photons because they strike H2 molecules and excite them. So if you include these UV photons and consider the so-called, the photoelectric effect due to these extra photons that typically are not included in models, we see here that the charging of the grains going from the outer part of the dense core to the inner part of the dense core is not just -1, as many people are always, say, assuming in these conditions. So you see a broad spectrum that goes from, say, -2 to +1. So you have a population of grains that are negatively charged, positively charged. And what this means? Well, this actually, it's important for also dust coagulation, because of course, if you have and it could either, you know, affect the dust coagulation in the sense that if you have, for example, mostly negatively charged grains, you will not, you will slow down the coagulation. But on the other hand, if you have, say, several population of grains with different charges, you can actually increase and speed up the dust coagulation. And this is important again because we are still talking about prestellar cores, so regions that are not yet formed, have not yet formed stars, but they actually contain the initial conditions. So at the very center of this course, in fact, we have found, also other people have found in, say, other clouds and regions, that if you look at various wavelengths in the millimeter, you can see that the dust opacity is increasing toward the center, and this is consistent with the presence, definitely, of thick icy mantles on one hand, but also using some simple modeling, as was done by Anna Shakontanaro when she was a student here, also, say, arrive at dust grains that are a few micrometer in size, even before forming a protostar. Now, cosmic rays are also most likely, and I will try to convince you that this is the case, actually produced and accelerated in early phases, in protostars. So this is a sketch coming from one of the figures of Marco Padovani's paper in 2016, where actually he does the calculation and shows which are the regions within an outflow, where you actually, once you have the protostar form, your disk, you have the ejection of outflows, and you have in some regions of this outflow acceleration of particles. So this means that we don't only have the, say, galactic and extragalactic cosmic rays, but we also have our local cosmic rays. And these cosmic rays can actually be so the flux of this cosmic rays can be very high, so predicted to be orders of magnitude larger than what is measured, for example, in diffuse clouds. So which is 10 to the -15, 10 to the -16 per second. So this is actually an important point because, again, if we look back at, for example, our solar system material, there is evidence that actually our young star, so our young sun, was actually was provided with these extra energetic particles. And these energetic particles, in particular, more than 10 MeV particles. So these particles can collide with material, especially in the inner edge of the protosolar nebula. And this, through spallation, can produce like short-lived radionuclei, like, for example, the beryllium-10, which is actually found in meteoritic material. What in 2014 was found and now confirmed with multiple observations with the NOEMA array that is shown here in its full glory. So here we have the work that Cecilia Ceccarelli did in 2014, showing that actually toward a cluster forming region nearby, there is evidence of large cosmic ray ionization rate, so 4 times 10⁻14. This was again recently confirmed with observations of other molecules that can trace ionization chemistry, but we never understood where this is coming from. So now finally, again, with the high sensitivity of NOEMA, we actually discovered, and this is work led by Valerio Lattanzi here, a very straight jet. So this is a jet, and you know that is a jet because it's SIO, and you see SIO only where is a jet because you need to destroy some of the dust. So to do that, you need the energetic, a strong shock that can actually sputter and destroy your dust. This is the continuum map, and this is the SIO map at the same scale. Great. So we have cosmic rays that are actually also local that we need to take into account. And these cosmic rays, together with the interstellar cosmic rays, are also important for the planet forming regions. This was shown in a very detailed work, again led by Marco Padovani and Alexei Ivlev in 2018, where actually it was done in, say, a study of the primary and secondary ionization. So you can see here, it almost look like, say, particle physics here, but this is actually what you have to do when you go in this dark region in the mid-plane of protoplanetary disks, where the densities are really high. Now we talk about 10 to the 12, 10 to the 13, 10 to the 14 per cubic centimeter, and things get really interesting. So here, doing this detailed work, what it was found was that the cosmic ray ionization rate in the mid-plane is actually higher than previously assumed. Previously, it was in fact just considered that, well, you know, it's not very important because maybe there is a modulation from the stellar wind and you don't get many of these outer cosmic rays inside. But actually, if you take into account the high energy cosmic rays, yes, you do. And this is the mid-plane cosmic ray ionization rate as a function of radius, log here. And here is for different types of protoplanetary disk, going from low mass, high mass, and these are all models that were done by Frank Shu years ago. And this is our minimum mass solar nebula. So you can see that actually you can keep relatively high, definitely say high level of ionization, significantly higher than the long-lived radioactive nuclei that is shown here, also in this mid-plane. So it's important to take into account these particles, not just for the chemistry, but also for the dynamics and of course, planet formation. So let me now move to deuterium fractionation. There is a nice link between cosmic rays and deuterium fractionation. I'm not going through that in detail because I have no time, but basically I'll just mention briefly. One thing that it's important for the deuterium fractionation, I want to go back here and look at the sea, that it's a long time I don't see now, and I really miss it. So the deuterium fractionation is obvious that is present in our Earth, because if you look at the water in our oceans, what we have is a D/H ratio that is basically 10 times larger than the cosmic D/H ratio, which is written here as the protosolar. So you see, this is 2, 1.5 times 10⁻⁵, this is 1.5 times 10⁻⁴. So how can it be? I mean, how you can have this high deuterium fraction? Well, first of all, if you look at these other things on this diagram here, you see that, well, here we have comets. Okay, they're all significantly higher than this D/H, except for one. So comets actually could have brought in the water, but there are also the carbonaceous meteorites that actually are spot on onto the Earth. line here, which are very suggestive that they are probably the ones who replenished our surface of the Earth planet with volatile, including water. So one thing that it's very interesting, actually, I always like to cite this paper that was published in 2014. It's a Nature paper by Ilse Klieve and collaborators, where actually they realize that no matter what, if you want to reproduce this high deuteration level, you have to bring in material from the prestellar phase. Because there is no way that if you start from scratch with atomic chemistry in the disk, there is no way you're going to reproduce this large D/H ratio. So in a sense, these confirm again that these early phases are really important, because that is where the raw ingredient and the storage is done, including the high deuteration. And this makes sense because we know that the deuterium fraction comes from a very simple reaction. And this is where actually the cosmic rays comes in, because to produce H3+, you need cosmic rays. You need to ionize H2 molecule first and let the H2 molecule react with other H2 molecules so you can form H3+. And H3+ is the one that activates the chemistry, because it can give the proton that is not very highly bound to other molecules and atoms very easily, actually to other atoms if you still have to start the chemistry. But here what it shows is that the H3+ can react with HD, so the molecular, the heavy H2, and form H2D+. And this is a reaction that is exothermic. And this was found actually many years ago by Watson in the 70s. Another thing that happens, and I already told you basically, is that in this region you have a large amount of freeze out, and mainly carbon, CO, and oxygen atoms, etc., are known to be heavily frozen out in these regions. So in the 80s, when the freeze out business was not yet known, Alex Dalgarno and Steve Lapp, actually with their imagination that had always say illuminated our lives, they told us that actually if you get rid of neutral molecules or gas phase heavy atoms like oxygen but also CO, you expect to have an increase, very sharp increase of the H2D+ over H3+ ratio. And this is simply due to the fact, as you can see below here, that the CO molecules that freeze out in these cold regions can actually destroy both H3+ and H2D+. And what happens with that is that you lower the H2D+ and H3+ destruction rate if CO freezes out. And at the same time, you make this reaction go faster because you have more H3+. The sum of the two makes this ratio very high. How high? Well, I mean, in our models, we can actually get as high as 1. So, you know, you get basically the same as H3+. And in fact, this is what we saw. I mean, we went to the top of Hawaii at that time to look for ortho H2D+, and we found a very strong line that actually helped us a lot to understand the chemistry, because we understood that now we really need to take into account deuterated molecules, and not just singly deuterated, but also doubly and triply, and this is what has been found also in later observations. So just to give you a little bit of understanding of what is going on, and is in a sense is a little bit of a recap, and also to understand the next stages. So we start with cosmic rays and H2 that form some dust grains. So basically dust grains and cosmic rays are the ones that we need, at least in our galaxy and the galaxies like our. You form H3+, then you have this exothermic reaction, and you form H2D+. This chain of reaction doesn't stop here. Of course, you can go up to D3+. It's not yet been detected, but D2H+ has been detected. We have detected a line with Sophia recently, and this is actually also very abundant. So what happened with these molecular ions? So on one hand, if they, for example, find CO or N2 in the gas phase, they can produce the CO+ and 2D+, and all these molecules that are really how to say, easy to detect and study. And these are the ones that give us information about this central region of the prestellar cores. On the other hand, when they recombine dissociatively with electrons, they produce deuterium atoms. These deuterium atoms are actually going to compete with hydrogen atoms on the surface of dust grains. So for example, instead of making methanol, you make deuterated methanol. And in fact, we see a lot of this deuterated methanol, not just singly, but also doubly and triply deuterated methanol. We see triply deuterated ammonia. We see HDO. The deuteration is really efficient, and you need to have this to have deuteration on the surface. And to have this, you need to have these molecular ions, and to have these molecular ions, you need actually to go back to these cold and dense regions. So what we see, for example, this is a relatively old actually compilation, but there is not much change in the past years. What we see is that the deuteration is significantly larger in organic molecules than, for example, water. This is what we see in star-forming regions. How do you explain this? Well, this was already predicted in a sense in 2011, and also by Cazot et al. And also Take et al. In 2012, that it's just a nice formation time. Why is that? Well, because first you have this, say, the clouds that forms, and you have your water ice that forms first, just because oxygen is very abundant in this molecular phase. You form water, but then only later on in the denser regions, you actually start to freeze out the CO, and the CO is what starts this complex organic chemistry, including the deuteration. So only later on, you actually form these deuterated molecules. So in these regions where they freeze out to cover, we go back to the Dalgarno-Lepp scenario, where you actually have very little gas phase heavy molecules that can destroy your deuterated molecular ions, and you form all these deuterium atoms that can deuterate your methanol, formaldehyde, etc. So this makes sense. And now look at this, and I thought this is, very interesting, and again telling us that there is at least a part of these early phases are kept in during all the process of planet formation, because these are some carbonaceous chondrites, and also in interplanetary dust particles, the IDPs. You see that if you look at the D over H in hydrated silicates, so this is mainly water, you see that the D over H is 10 times larger than the cosmic D over H. And this is in fact exactly the same as our terrestrial ocean. But when we look at the hot spot, when we have the organic molecules present, you see that the D over H can go up even to, say, 1%. And this is in fact consistent with what we see in interstellar medium. Right, so at least some of these ices will be kept. So it's important to understand these initial conditions, because of course you can imagine the problem is very complex. So without the proper knowledge of the initial conditions, we are basically lost. So we go now to the complex organic molecules. This is a beautiful picture coming from, again, the Herschel spectrum, high-fi spectrum of water and organic in Orion Nebula. This is the Hexos team led by Ted Bergin, where of course they look at, say, Orion and other star-forming region, and found very high, very bright lines of all kinds of organic molecules and prebiotic molecules. Great, but how these molecules form? So can they actually form already in these early phases where there is no star, there is no heating source? So if we look at that, this is now a study led by Silvia, and she's continuing these now with more and more, sensitive observations done with the IRAM 30-meter telescope. And this is, again, our core, our laboratory in space, where we see that, so the dotted lines here is the continuum, the dust continuum, the peak of the dust continuum. And now here, depending on which molecules you're choosing, you can see different structure, different morphology. But this is the beauty of astrochemistry. Basically, each molecule tells you a different piece of your cloud, of your region, and then you can build up a 3D picture that otherwise you can't do that with other things. So what Silvia found was, well, the nitrogen-bearing molecules and the say light ions, as we saw before, they are peaking toward the center, and they are just following the dust. However, if we look, for example, at methanol, remember methanol is formed on the surface of dust grains. The methanol completely peaks in a different region. And then we have the carbon chains that are also very important, that for the chemistry, they are peaking actually opposite from, so if you look at this triangle here, like the peak of the mountain, methanol is on one side and the carbon chains are in the other side. And this other side is actually the side where you have the most illumination. So what we are showing here is this region here. This is the side where it's actually getting all the UV, interstellar, UV field here, and you have dissociation of CO molecules, and here is more protected, and you have basically CO forming, CO freezing out, methanol forming, methanol desorbing from the surface, because we see this methanol in the gas phase. With the 30 meter again, I mean, if you really look deep, like Itascon did in 2016, you can then see all kind of chemistry. So here you have, depending if you pick at the, if you look at the core center of the methanol peak, you see also different chemistry. So nitrogen-bearing complex organic molecules peak toward the center, as all other nitrogen-bearing molecules. Oxygen-bearing complex organic molecules peak outside, in particular toward the methanol peak, as you can see here. These are pretty big molecules that basically were not found before, only toward these hot cores or regions where that are very close to protostars. So again, this initial chemistry starts early. And now we have a new paper led by Jorma Harju, who has been still a long-standing visitor here. So he did these beautiful maps to understand better, because now we need, of course, the interferometers to understand the structure of these molecules and what they trace. Of course, this is important because then when we look at the line profile, when we look at the dispersions and want to reconstruct the kinematics, you need to know where you're looking at. Otherwise, it's very complicated. So what Jorma did is using ALMA and look at the deuterated ammonia that traces beautifully the prestellar core, this inner, very, dense and cold region. But the methanol, you see here, is just tracing one side, following and basically connecting to the cloud that is in this region here. And what is clear, again, as Silvia found with the 30 meter, also with ALMA, we can tell that so these complex organic molecules surround prestellar cores and prefer their dark sides. So now we know where they are, and we can then put things together and understand how also these cores form and interact with their mother cloud. However, we also want to understand how these molecules forms. So for this, we had Anton Vasyunin, who has now a Max Planck research group in his town in Russia, where he has, so when he was here, he actually built up a chemical model taking into account gas phase, grain surface chemistry, and also the fact that you may have some changes in the binding energies of molecules and also in the desorption of molecules. So when they form on the surface, because when you form a molecule on the surface of the grains, you get some extra energy, and this extra energy, at least part of it, is used by the molecule to go back in the gas phase. This is what H2 molecules do, for example, so why not other molecules? So what Anton found is that actually when you arrive at the region of the cloud where you have CO freezing in, so you have a region where you encircle this CO freeze out region, what you have that is where CO start to catastrophically freeze out, is where the CO started to be hydrogenated, and the reactive desorption actually produces this large amount of methanol and also complex organic molecules. And you can see here, this is a fractional abundances of various species that are written here. And then this is a function of radius of the dark cloud. You see that with the time you start to have freeze out toward the center, and the peak is actually at about 0.01, so almost 0.1 parsecs away from the center, and this is very close to where we actually found our methanol peak and complex organic peak. So at least this is something, of course, they still work in progress, because there's still lots of things to implement, but at least overall we understand what's going on. And what's going on when a protostar is formed. So we arrive there, so assume you are a dust grain, you arrive close to where the protostar is forming, and you start to get a bit kind of warmish, and then pretty warm, and then the ice will eventually, say, evaporate if you get very close to the protostar. So what is the temperature that you need? Well, you need, for example, about 100 Kelvin for water ice, which is the hardest in a sense to evaporate. And so you really need to go close to the action where the protostar is forming. Of course, you can also actually release molecules in other ways, for example, along outflows, because you have sputtering of ice, and in fact, the complex organic molecules have been found also there. This was the first work by Hector Arce and collaborators that actually found complex organic along outflows, and you can do that if you sputter ice along these outflows. And this has been sorted out, at least theoretically, so with say papers like my work in '97 that I did with Tom Hartquist. Actually, I started that here at MP when I was a postdoc at that time here, just for a few months, and then Jimenez Serra and collaborators did more work on that. So again, you know, I never forget that we wanted to understand how much of this material it can actually be incorporated and transmitted to later stages. And this is actually work by Maria Drozdoskaya and Evina van de Suk and other people, Katrin Altweg from Bern. They actually put together the work done by Jess Jorgensen. This is the beautiful field survey that is basically a spectral line survey done with ALMA in one of the youngest star-forming regions. And here you have the abundances of organics, complex organic molecules for the young protostar and for the comet. This is the very famous comet that was visited by Rosetta, 67P, was visited by Rosetta not long ago. And so you can see actually a very good, pretty good correlation between the two, again telling us that, as they write in their paper, the volatile composition of cometesimal and planetesimal is partially inherited from the pre- and protostellar phases of evolution, which is also very interesting. So in some way, some of this material is protected and say maintained all the way down. Another interesting work, this is actually also, we have been part of it, and there was a press release. This is putting together again Rosetta and actually Rosina. This is the spectrometer that was able to say measure which components are present in the ice of the comet. So what was found is that there is quite a lot of phosphorus in the comet, and in the form of PO, which is also the most abundant molecule, P-bearing molecule in the interstellar medium. And this is, it's very important from my point of view, because the PO is an easy way to actually deliver phosphorus in the early Earth environment. Otherwise, phosphorus is stuck in refractory material in rocks. It's very hard to get out of that. But if you deliver that together with other organics and water, maybe this helps a lot actually to provide the initial source for the phosphate group that is needed as the group that actually attach together the various steps of the ladder of RNA and DNA. Right, so now we have this, you know, we go from, say, cloud to solar system. There is a lot in between. And of course, we need to work on that as well. And we need to connect the dots. It's hard, it's not easy, but we put all our effort there. And this is, of course, thanks to many people, of course, the CAS team, including people working in the lab that provide the very accurate frequencies and also say measurement of ICEs and opacities for ice. But in any case, what we need to do is to connect the cloud to the disk. So how do you do that? This is again an interesting question, because it has been shown since several years that actually it's not easy at all to form a disk, because you have a cloud that is magnetized. So assuming that you have a flux that is frozen in your cloud, you are not going to make your disk, because it's very hard, because when you get to the disk size, you have so much frozen magnetic field that you lose angular momentum through the magnetic braking effect that is known since many years. So how do we do that? So of course there is a lot of theories, people who will think about, you know, including turbulence, but we always have to be careful because we don't see much of this turbulence in these clouds. The lines are narrow. Everything is very quiescent, at least at the beginning. Of course, if you make a star, then, you know, nearby things get stirred up. But if you want to make it at the beginning, your disk, you need to take into account other things. So we think that probably disks at the beginning are gravitationally unstable, making, say, these beautiful spiral arms. And then, of course, there is interesting chemistry going on. I'm not going into that because I have no time. But what I want to show here is that, again, taking into account the microphysics correctly, following a simple chemistry that includes the ionization, the charging of the grains, as we have done in the past years, can give us some hints of what is going on in these regions. And this is work led here by Bo Zhao, who has done run a lot of simulations of basically prestellar cores contracting, magnetized prestellar core. Here we have also non-ideal MHD effects, and we take into account some chemistry, and so to try to follow the ionization as much as we can. What Bo found is that if you keep, for example, the dust grains as the ones that are present in the interstellar medium, Matisse round North-Sea distribution, MRN, you have actually a hard time to make your disk, because these very small grains, so the ones between 10 and 100 angstrom, are really well coupled with the magnetic field. And as I was saying before, they basically drag the neutral down and they slow the contraction, the rotation during the contraction. So once you remove, if you remove these very small grains, for example, as we wrote in that paper, could be that these very small grains could be considered like big molecules, so they just freeze out on top of larger grains, then this reduces a lot the magnetic flux in the inner region. You actually enhance the ambipolar diffusivity and you get your disk. And in fact, you can see here, without very small grains, you can actually form some of these self-gravitating disks that we were talking about before. And also here, with the very small grains, you actually form a mass. So you have basically no disk at all. And so no planets going to form in this region. And it's so very messy outflow as well that is coming out from the disk, so from the plane here of the simulation. Now, the question is it true that these very small grains are actually disappearing from the gas phase in these early phases of disk formation? Well, Kedron Silsby here, he just submitted a paper that shows theoretically that yes, the answer to the question is yes. So you can actually deplete very quickly these very small grains, just taking into account the non-ideal effects that you have during the contraction of a cloud that contains, that has magnetic field and some ionization. So you take into account also the ionization of the grains, the charging of the grains, and he found that it takes very short time compared to the dynamical time scale to actually get this dust, very small grains out. So we think that this is a very promising way to actually understand how you can actually form disk. The other thing that I wanted to highlight here, I see now the time is getting a bit late, so is the fact that actually if you think about these large grains, that some of them could be PAHs, so these rings of material, they could be in fact the originators of the IOM, so this insoluble organic matter that is seen later on in our pristine material in our solar system. So now I will move a bit fast, just show you some pretty picture. For example, here, depending on again on the initial conditions that are very important, you can reproduce all kinds of disks that are observed with Bose simulation, including, for example, also the super high resolution work that was done with Felipe, with Alma, and here is our pretzel that was published in the ESO press release during the Oktoberfest last October. And here you see this interconnection of filaments and structure. In this case, you have these little disks that are the size of the asteroid belt in our solar system. And another thing that I'd like to highlight, because it's a beautiful result that came out from NOEMA, and actually these tell us how NOEMA can be used as a real synergy, also say together with ALMA, but in this particular case, it's just by itself, it gives us a lot of information. This is the work by Jaime that shows that NOEMA actually found this very long filamentary material in carbon chains. So this means that this is material from the outer part of the cloud. If you remember, carbon chains come from the part that where there is not much CO because you have irradiation. So the other part of the cloud that connects directly into the central region. And this is the dust continuum that is seen with ALMA. But you see that with NOEMA, we actually see everything, we see the connection. And this is the important thing, the important message that I wanted to give about the fact that we really need to connect these scales all the time, because otherwise we can't understand how, for example, you can provide more material, you can actually understand how the chemistry evolved and changed without taking into account these flows of material. There is a preliminary result from a larger project that are also very promising, very beautiful, that shows again that we can now use molecules to understand very much in detail the inner size of the envelope, where we can study the connection to the cloud and the outflow from protostar. And then, of course, we come to protoplanetary disk, that there is a lot of work done, of course, by other groups, but also here, Dominique Segura-Cox has just submitted a paper that shows actually that these rings that are found in relatively evolved disks are actually also found in very early stages of evolution. And this is, we are talking about, you know, a protostar of 100,000 years. We already have rings here that most likely are, say, the precursor of, you know, the future planets that carve these disks. Okay, so now, because my time is basically out, maybe most of you have left already, I just wanted to conclude saying that, you know, also when we look at disks, this is work done by other people, we have this connection between the chemistry of say, comets and the chemistry in disks. There is always very much, so starting from the clouds down to protoplanetary disks, down to comets, we see this very strong connection in the chemistry. And one thing we need to work on, this is also work for coming from Richard Teague and collaborators, from Michigan that showed that actually you can see that you don't have to take into account only, you know, the mid-plane composition when you look at the formation of planets and, for example, formation of exoplanetary atmosphere, but also you have to take into account these meridional flows that are found. These are the velocity arrows that are actually coincident with these rings that are found in this specific star, which is HD 163296, one of the famous stars, Herbig stars with rings, and shows that you have this meridional flow. So you have to take into account also the accretion of this volatile material. So, and from this on, you know, we arrive at this connection to planets and exoplanets. This is, of course, the future also that we want to understand and connect. There is already a lot of activity. We are very lucky here to be, you know, at MPE, because already with the gravity, there have been beautiful results already on direct spectroscopy on, say, young planets. And of course, the future is very bright, because also the ELT will provide the important contribution to that. JWST, this is another spectrum that was done by Madhusudan, like a synthetic spectrum showing how many molecules actually you can detect also with JWST. But, you know, also for the far future, I would say, even exobiosynchronous, we need to take into account, and definitely the people who work in exoplanet community, they know this already, and they will definitely target the TRAPPIST system that is relatively nearby, and we can then look at those that are in the habitable zone. So I finish here. I cannot believe it took 1 hour, but I would say that there are many things we have learned in the past year, and we are now at the stage that we put things together in a, say, it looks like a puzzle, but now we are putting the puzzle in place. We understand that these early phases of star formation are really important, both for the production and storage of chemistry that later on is found also in our ocean or in stellar systems. Cosmic rays are with us all the way from, say, the very early phases to late stages. We need to take into account dynamical processes. We can't just take the disk and think that the disk has been there alone forever. We need to actually take into account that this disk is fed not just by the inner envelope, but also by the mother cloud during the time of formation and evolution. This, I'm sure, it will change a bit the vision of how, say, planets, say, will form later on and their composition. And one point that I want to make clear is that to really connect this chemistry with the exoplanet atmosphere, we need to do not just, say, grain growth and chemistry. We need to mix up these things and also study how the dust, say, changes in structure and composition together, of course, with the gas and the 3D MHD with chemistry. So a lot of things to do, but of course, very exciting, at least for me. And I hope also for my great group that I show you here. These are students, postdocs, senior researchers, everybody together that helped me all the way. And without them, of course, I was not here telling you what we have done. So thank you so much for staying with me.
Thank you very much, Paola. If there are any questions, please write them in the chat.
Should I stop sharing, or?
As you prefer.
Oh, it's okay, I stay here with them.
So we have the first question. What is the energy range of the cosmic rays being produced in the protostellar jets? And for these energies, is this the dominant mechanism galaxy-wide?
So we are talking here about mostly low energy cosmic rays. So, and these are probably the ones that are, say, maybe providing the low energy part of, say, of the cosmic ray spectrum, which is in fact not easy to understand if you just take into account galactic cosmic rays. But they're very important because they are the ones who actually, you know, provide the ionization and the heating also in these regions. Of course, you should look at Marco Padovani's paper in 2016, the one that I show you, because that is where you can find all the details of the acceleration processes, etc., that are described in detail there. And there is still, I think, a lot to do especially for the connection of these energetic particles with the disk, because I think that is really important. So I hope Marco will do it at some point soon to connect, because of course this could change also, in a sense, the ionization structure of the disk that so far we have only been considering the external cosmic rays.
Okay, any other questions? Okay, so the question is from JB. Is the production of cosmic rays by protostars invoked here testable or tested with high energy experiments? In brackets, it's written, I understand galactic magnetic fields might make this difficult.
So with experiments, so I mean, if it is, with observations or with experiment as well. So anyway, I can say that yes, we can, for example, this early work that was led by Ceccarelli in 2014 was the first where actually was found that there is a hint of super high ionization nearby a star-forming region. So through the chemistry, you can actually say, find out that there is some source somewhere. And now, as I showed you before, you can actually see that there is in fact a jet in the direction, in fact, where we see this higher ionization, larger ionization that is telling us that indeed this picture that was built by Marco Padovani is right, and it could give actually a proof. Of course, the other proof is also to have synchrotron radiation detected, and in fact that is also what has been done recently by other groups. So there is evidence for that. And what do they do experimentally? I mean, what do they do, for example, in detail to the microphysics that can also be tested in experiments? And in fact, this is what we will do if our proposal will be accepted. We actually, yes, we will do this soon.
We have another question from Roland Thiel. Would the cosmic ray excited material lead to diffuse nuclear line emission that we should look for as diffuse galactic signal? We might be sensitive enough for diffuse signal only.
I don't know. I cannot tell this because I didn't actually look into this about, so if you have some, say, specific you know, nuclei that you can form, or the only thing we know is that, you know, in our solar system, as yeah, Roland knows, there is the evidence that this radiation has been present and formed, in fact, these radioactive nuclei that are also in our primitive materials. So, like the beryllium. For the diffuse, I cannot tell. I just, I need to study a bit.
Roland is writing 12C would be excited.
Okay. Right, yes. Well, 12C is not easy because atomic carbon is basically, if you try to detect atomic carbon, you see everything. And it's not easy because you need to disentangle the various region of of your galaxy, basically. So maybe in extragalactic, that could be a good idea. Mm-hmm.
We have another question from Tim Lichtenberg. How do chemical compounds found in the ISM translate into compounds at the surface of young terrestrial planets to participate in prebiotic chemical networks? Can we make a direct one-one connection between these two stages?
Well, I mean, it's it's a difficult question. It's a good question, and in fact, this is something we have been trying to understand, making this correlation between the composition of material in star-forming regions or planet-forming regions, like in protoplanetary disk, and the comets and or meteoritic material. Of course, in meteorites, the chemistry is so complex that unfortunately we have not detected all the molecules that are present there in space. But from what we have learned so far, I can tell that there is a very good correlation between the composition, say, of comets and the composition of young stellar objects, and when you look at all these complex organics, and also including the deuteration fraction, and also including the other fractionation that I didn't have the time to talk about, are also very interesting, like the 15N. So there is evidence that something quick must have happened, that you have the formation of these ices, thick ices, and then you go from having these tiny little particles into larger pebbles and rocks in a relatively short time scale. This is, from what I think, is a good way to actually prevent the evaporation and super processing of the ices that we see. And then, of course, if you still have replenishment of material from the mother cloud, as we saw with the work of Jaime, you can keep bringing in this, say, cloud material also at later stages in the formation of the disk. So we are getting there. So you see, I mean, it's I'd like to say yes, we do, but I can't yet, definitely. But I think we are on the right track to actually say that something is in that direction. And that is not just with the complex organic, as I said, is with the fractionation, with the phosphorus, and also with the noble gases that has been also shown by Katrin Altweg and people who have been looking in detail at the comet, the 67P.
Are there any other questions? I don't see any new questions. Let's see.
It's okay, it's very late.
Yeah, so I don't see any question. Paola, thank you very much again.
Well, thank you all for helping, and also all the people who have been connected. And yeah, I see some good friends and colleagues. So I just, as I said at the beginning, I wish to see you all very soon. Bye-bye.
Bye-bye.